Now each video is divided into a 15-minute block. You should study this 15-minute block and then take a break and try some problems. And then when you're ready, continue. Now what I have here, this is a DC power supply. Now this particular power supply was used to provide a DC voltage to a notebook computer. This is another DC power supply. It's a very simple one. This DC power supply was used to provide a DC voltage to an answering machine. Now, it's a little difficult for you to see here, but look, what we have is we have a transformer, and then we have 4 diodes forming what is referred to as a bridge rectifier, and then we have a smoothing capacitor. It's this capacitor that's used to give us that DC voltage. These are interesting. So look, let us continue our study on diodes. So really what I want to try to do today is really develop an understanding of these clipper circuits and a way that we can actually deal with these. So we'll really try to develop a methodology here. All right, so let's take a simple clipper circuit. So what we have, in a moment I'll talk about this source in just a second here, but we have a voltage source. This voltage source is going to be, in our case here, a sinusoid. Then we have a diode, and we're just simply going to take a very simple circuit here with one resistor, which we're going to call R. That's the circuit that we're going to try to analyze. Now look, let's call the output voltage here VO, and let's call this input voltage over here, we'll simply call it V, if you like, in for the input voltage, and we'll define the reference plus minus. Okay. Now what we're going to be doing here is we're going to be using really the second approximation for the diode, All right, if you look at what that second approximation is, then we had what? We had a graph of ID versus the voltage VD, and the second approximation looked like this. We had a characteristic curve which was parallel to the vertical axis here. And in the case of silicon, this value of VD was 0.7. Now in our problems now, we'll assume that we're dealing with silicon. Okay, so that was the second approximation. Now V in this particular case, we're going to assume is a sinusoid, and we're going to assume in our example that it has a peak value of 10 volts. Okay, so V in is a sinusoid having a peak value of 10 volts. Okay, all right. Now what is our task here? Our task is really to determine the output voltage as a function of this input voltage. So as this input voltage varies, how does this output voltage change? All right. I want to look basically here at breaking this problem up into 3 cases. The first case is where we determine what I'll refer to as the onset of conduction, when this diode is just about to conduct. All right, on our characteristic curve, it would equate to being at this point right here. Then we'll consider the case, values of V in, where the diode is conducting. And then we'll consider the case that those are values of V in where this diode is not conducting. All right. So our first step here then will be what I'll call case 1, and we will try to find the onset of conduction. Okay. All right. At the onset of conduction, the voltage across the diode VD will actually be equal to, will be right at this point here. So the voltage VD will be equal to 0.7. And the current through the diode, ID though, will actually be equal to 0. We haven't started to conduct. We're right at the edge of conduction. We're right at the onset of conduction. All right. Now what we're trying to do is How big do I have to make this V in to bring me to that edge of conduction, that onset of conduction? All right, let's label this circuit. The voltage here, plus minus, of course, is the voltage across the diode VD. All right, what we're going to do with this problem in this first case is we're going to take a loop, okay, and we'll see if we can find the value of V in required to bring us to this point, to this onset of conduction. So look, here is our loop. Let us go round that particular loop. All right, I'll start here. Okay, as I go around the loop, what do I have? Going from a minus to a plus, I'm going up. I have V in, all right? From here to here, the voltage across the diode, I'm dropping, so that's a minus VD. And then, of course, from here to here, what is that? That's dropping, so that must be a minus VO, all equals 0. Okay, now let's consider some things here. At this case, for this particular case, which is the onset of conduction, the voltage across this diode is 0.7, but the current through it, we're right at this point here, is equal to 0. All right. If the current ID is equal to 0, then the voltage really across that resistor must also be equal to 0. Remember, the current, it's a simple series circuit, the current is flowing like this, so that current being 0 means that that voltage is 0. So because ID is equal to 0, V0, the output voltage, will be equal to 0. So that really simplifies what we have here, okay? All right, let's put in this information. V in, then, minus VD, which is what? 0.7, minus VO, but we said that that is 0, all equals 0. Okay, so there's our basic equation. So therefore, what does V in have to equal to bring us to the onset of conduction in this example? Well, if I take this to the other side, then V in would be equal to 0.7 volts. And so really that is our first case. We had to bring V in to a value of 0.7 to bring this diode to a point referred to as the onset of conduction. So that, if you like, is case 1. Remember, there are 3 cases, okay? Case 2, we might assume then that the diode is conducting. So that means if we make V in greater than 0.7, the diode will be conducting. So let us consider this, if you like, case 2. All right. So we'll call this case 2. This is when V in this particular problem is greater than 0.7. Okay. Diode is conducting. And let's see what the relationship then between V in and V out is for this particular case. So look, let's go ahead and redraw this circuit. Okay, so it's a simple circuit. There is my sinusoidal voltage, V in. Here is my diode, and here is the resistor. Okay, and I'm measuring the voltage VO across that resistor. Okay, let's just label this again, plus, minus, that's the voltage across the diode. Okay, what's our condition now? V in greater than 0.7, diode is conducting. If the diode is conducting, then the voltage across the diode, using that second approximation, will be equal to 0.7. What about the diode current? Well, the diode current, we can clearly say that that is not equal to 0 in this case. Not equal to 0. If once again I looked at the characteristic here for that second approximation, there's VD versus ID, then we are somewhere on this curve, on this vertical section of the curve. Okay? All right. Once again, what are we going to do? We're effectively going to take a loop. All right, so let's go around the loop. What do I have? I have V in, okay, going up. I have minus VD, and then of course dropping here, I have a minus VO, all equals 0. VO is clearly non-zero because the current is non-zero. Okay, if I take the VO to the other side, then I have V in minus let's put in the value of VD now. What is it? It's 0.7, so it's minus 0.7 is equal to this output voltage VO. So there is really my relationship now between the output voltage and the input voltage. The output voltage is really equal to the input voltage, but just 0.7 less than. Okay, so we're basically deducting 0.7 from the input voltage to determine the output voltage. And look, that is case 2. All right, let's now look at the last case. All right, and the last case would be what? Case number 3. And here we're looking at now the diode is not conducting, so V in now, let's say, less than 0.7 in this particular problem. The diode, if you like, is not conducting. Sometimes we can refer to that as being the diode is off. It's not conducting. It's like an open switch in this case. All right, let's draw our circuit again. Here is our circuit. There is V in. Let's define that plus. Here is the diode in the circuit here. Plus minus the voltage VD across the diode. And once again, here is the resistor. And here is the output voltage V plus minus. All right, now how do we deal with this problem? Well, if V in is less than 0.7, the diode is off, we can clearly say that the diode current, the current in that circuit, is actually equal to 0. If the current in the circuit is equal to 0, then of course the output voltage really must be also equal to 0. So for any value of V in that's less than this 0.7, in fact it's less than or equal to the 0.7, basically this output voltage here in fact is really equal to 0, and we've really effectively analyzed that particular condition. Okay, now you could have taken a loop around the circuit. If we'd taken a loop around the circuit, gone round the loop, you have what? V in, okay, then you have the drop here, which would be what? It would be a minus VD, and then you have a minus VO, all equals 0. Okay, well we know that VO is actually equal to 0. We don't know this value of VD, but we could find it if we put in a value of V in and solve the equation, noting that that term has in fact gone to 0. Okay? Didn't really need to take a loop in this case because the problem was pretty obvious. If the current is 0, then the output voltage is 0. So any value of V in less than this 0.7, this output voltage is in fact 0. And that is that case. Now the last part might be to take these 3 conditions then and basically draw, if you like, a relationship of the output voltage versus that input voltage. So let's just have a quick go at doing this. All right. So what we have here is, if you like, the input voltage. Now this will be a fairly crude drawing on my part here, but let's just draw it. Here is the input voltage looking like this. Of course, it has a peak value of 10 and a negative peak of minus 10. It is a sinusoid. Now our task then is to determine, well, what's going on really with this output voltage really as a function of time. Well, once again, let's put in our 3 cases. Look, case number 1. What was case number 1? Onset of conduction. So that was the onset of conduction. Then V in had to be brought to a value of 0.7. And of course, the output voltage was what? 0 for that case. Case 2. Okay. Well, that basically said that when V in is really greater than that 0.7, the output voltage was basically equal to the input voltage minus a 0.7. That was case 2. And then finally, case number 3, that was when we said let V in be less than what? 0.7, the onset condition. Then, of course, the output voltage, because the current ID in the circuit was 0, the output voltage was also 0. So those are our 3 cases. All we're going to do is plot these cases on this graph. So if we look at the, if you like, the graph for V in, what are we saying? Let's put the onset of conduction there. V in had to reach, okay, and it's not to scale, but it really had to reach this value, which we'll say over here is 0.7. Not very clearly shown, but look, there is 0.7. So when V in reached 0.7, okay, we're at the onset of conduction. Now we can come along here, note it's there, come along here, make a note here, and so on. All right, now let's take some information down to the output graph, like so, and like so, and like so, and like so. All right, so what are we saying here? When V in is greater than 0.7, that's in this region right here, and this region right here, what is the output voltage? The output voltage is the same as the input minus 0.7. So really what we're seeing is an output voltage that looks like this. It doesn't reach a peak of 10, it reaches 10 minus 0.7, which is 9.3. And so we see peaks looking like that. All right, last case to plot on this graph. When V in is less than 0.7, that's this region right here, this region right here. What's the output? The output is 0, and so the output is 0 along here. The output is 0 along here, and the output, of course, is 0 here. So what we have here is basically a half-wave rectifier. It's a clipper. We've chopped off, if you like, or clipped off the negative going part of the waveform. Now, this is a particularly useful circuit in building a little DC power supply. All right, in a moment, what I'd like to do is for you to pause this tape. This is really pretty much the end of this block, but I'd like you to have a look at a problem before you restart. I'd like you to take this particular problem, and I would like for you to produce a graph, okay, of basically that output voltage versus the input voltage. See if you could do this. What are you doing here? You're taking the three cases, the onset of conduction, diode conducting, diode not conducting, and you're seeing if you can draw a graph. This particular graph is useful because it's called basically a transfer characteristic. Okay.